Hello and welcome, not to another episode of How to Understand X, but a continuation of an existing episode, that one being derivatives. I unfortunately did not have the time nor energy to go through some of the more, I wouldn't say uncommon, because you'd probably have to do some of these derivatives at some point, but maybe some things that might seem a little bit more advanced until you actually think about it. And, you know, I will do like an application of the derivative and of the integral video in some capacity in the future. So don't worry too much about the applications. We're just going to be talking about how to do those derivatives. And I think I'll do, you know, logarithmic functions with a base other than e, exponential functions with a base other than e, and trig inverse, maybe like derivative, determinant. We're just going to be covering stuff that I didn't cover then. And also, most of, I think, I'm not sure if it's all, but definitely most of the proofs that we're going to be doing today require some deeper understanding of implicit differentiation, which I I did a disservice to. I didn't explain it as much as I should have, and for that I apologize. But essentially, I I feel like I might actually do a little segment on that. I'll have to like organize my thoughts and really make a good like thing, because implicit differentiation, I feel, is like, it's not a hard topic by any means, but it's something that I did have struggles with when I was learning it. But still, um, implicit differentiation. So most derivatives that you do, you use this notation. You say f prime x, or like some function of x, like x squared plus 3x or whatever, prime. These, I'm not going to say f prime x. That was wrong. F of x, that is a function of x. X squared plus 3x, that is a function of x, and on and on and on. These are all functions of x. And you can find the derivative with respect to x of, I'll go back to our x squared plus 3x. You can find the derivative with respect to x of that, and you can find the derivative with respect of this by just putting a prime. That's considered the derivative of f of x with respect to x. But say we introduce another variable. This does not make it multivariable calculus, because we still have our x and y axes that we're working with. We're not expanding any further, at least for now. But still, if we introduce y, we have to do something called defining this y. We can explicitly define this as a function of x. And that's what happens on most graphs. You say that y is a function of x, and then f of x is equal to like something like that. Or you can skip f of x entirely and just say, hey, if y is equal to like x squared plus 3x, going back to that first example, it's obviously a function of x. It varies as x varies. So yes, it is a function of x. But those are both examples of explicitly defining y as a function of x. And implicit differentiation, you are not doing that. I'm not going to use the same example that I did, but you are saying that y, you could, like, I guess I'm going to use an example. So ignore what I just said. You could y cubed plus, like, I don't know, x 7 y 1/3, something crazy. If you wanted to, perhaps you might be able to figure out some way to isolate these y's and explicitly define it as a function of x. But that is very, very difficult to do, especially with as many different components of this kind of term as we currently have. So we can implicitly define y as a function of x. We can say that, hey, obviously, y is a function of x. I don't even need to say that. I'm just going to treat y as a function of x, and therefore use the chain rule to find the derivative of y. Because, again, we didn't explicitly define y as a function of x. If y was a function of x, then we could, do our normal derivatives. We'd be like, oh, y squared, that's just going to be 2x, because y is basically x, and that's not something that we can do. We have to say that y is its own thing, but in our heads we're like, yeah, y is a function of x. And so we're going to have to use chain rule for that. I will go to our f of g of x notation, but I'm going to change that very quickly. If you remember chain rule, it was f prime g of x times g prime x. That's saying that if you have some function that is a composite function in which f of g of x prime is what you're trying to find, then that would be f prime g of x times g prime x. But what should we do here? I'm going to not use this notation right now, because even though that's what we worked with so far, I feel like it can get a little bit hard with implicit differentiation specifically. So I think maybe we can use the h notation. We can say that h of x is this function, and h prime x is equal to all of that. And remember, h prime x is the larger function that takes in g of x as the input. So that's our first thing. And g prime x is the smaller function, or like the thing that takes in only x as input. So if we adapt this, we can use our dx notation that we may or may not have dabbled in, but du dx. We're going to say that u is a function of y, which is a function of x. So I know that's already kind of weird sounding, but still, it's like saying u is y of x, which is exactly that same kind of style. I would use df and like g, but I feel like that might get, a bit weird, because you won't see those very often in like textbooks. But du dx, I think, is the most common. Du dx, if we say that u is a function of y, which is a function of x, then we could adapt our chain rule to say that this would be du dy if y of x is our input for u of x, then y of x would fit that, and u prime, or the derivative of u with respect to its input, and our input's unchanged in that one, so it'll also be unchanged here. It would be du dy, and then this is multiplied by g prime x, which is y prime x in our new example. So it'll just be the derivative of y with respect to x. That's nothing new. Dy dx. This is chain rule, and this is really important when we're doing implicit differentiation. You are saying, hey, if we know that y, or we actually don't know, but we're thinking, hey, maybe y is a function of x, then we can say, if y is a function of x, let's just try and differentiate it normally, but acknowledge that since y is not explicitly defined as a function of x, we would have to multiply it by the derivative of y with respect to x, just to make sure that we understand that y is not explicitly defined as a function of x. And so, you can't just differentiate y squared into 2y and then not multiply it by dy dx. So yeah, if you want to look at maybe an example, you could look at the other video, but I think that's probably as good of an explanation of chain rule as I can come up with. And we're going to do a pretty simple proof right now. We're going to say log ax. I'm not even actually going to show you the final step of that because I think you can just like follow the steps and we'll see it together. So we are going to use our logarithm rules. Is that the correct way to say it? I don't know. But log base a x, or I don't know how to say it. I think it's logarithm of x with base a. But you can correct me in the comments down below. That is equal to ln x over ln a, or log e x log e a. And that's just saying, if you have, if you're trying to split a logarithm from its base, then you can divide the logarithm itself by the logarithm of a base if you have a common base, that being e for us right now. So log ax is equal to ln x divided by ln a. And already, let's define this as a y. Let's talk about implicit differentiation for this one specifically. We're gonna try and find a. Actually, does this need implicit differentiation? I don't know. I don't think so. Never mind. Okay, so we're just gonna factor out this 1 over ln a from ln x, and y prime. 1 over ln a is going to be a constant right now. And, ln x, we spent a long time talking about that. That derivative is 1 over x. And, yeah, that's pretty much it. This is just going to be 1x ln a. Yeah. Did I do something wrong? Wait, let me check. No, I think that's it. Yeah. Since 1 over ln a is a constant, we can just factor that out, and we don't have to take the derivative of that. So yes, the only thing that's being derived or differentiated is 1 over x. I knew that the end result was the same, but I thought there would be more steps, and I thought I messed something up. But yes, that was the proof. The derivative of some function log base a of x is going to be 1 over x ln a. And yeah, that's pretty much it. On to the next one, I guess. We're going to be talking about the derivative of some exponential function with a base other than e. And so for this derivative of an exponential function with a base other than e, we're going to counterintuitively rewrite our derivative of e to the x, which, again, is just going to be e to the x as well. And using chain rule, if u is a function of x, then the derivative with respect to x of e to the u is going to be e to the u times u prime. But still, if we think we're trying to find the derivative of a to the x, right? How could we make this into some derivative of that? Or not derivative, math derivative, but like some offshoot of that. And I think that might go to another thing that we were talking about. We know the derivative of ln x, and we know the derivative of e to the x. So we could, do some fancy math stuff, figure out some derivatives using those. But I don't think we're gonna have to do any derivatives of ln x specifically. But you'd need to know that ln is the inverse of e. So what we're gonna do is we're gonna say that a to the x is equal to e to the ln a, or not a to the x is equal to that, but a is equal to e to the ln a, which is true. It's like saying a squared, square root of a squared is equal to a. You're just doing a function onto it and then using the inverse of that function to cancel itself out. And yeah, so let's try and figure out what we're doing. We know what a is now in our newly defined terms. We have d dx. Honestly, I don't think this needs implicit differentiation either. Okay, I promise we're gonna use implicit differentiation at some point. It's definitely gonna be for the trig inverse ones, but I just have not been planning properly for this video at all. So d dx is of a to the x is equal to d dx e ln a to the x power. And that's just what we're saying. If we say that, if we're saying that this is a, then a to the x is obviously going to be that to the power of x. And if we were to do some type of derivative of this, what we would have to do is use the chain rule. Let's think. So e to the ln a to the power of x. Well, we're not going to use the chain rule right now. We're just going to simplify this exponent a little bit. We're going to say that any thing times, not times, but any power to a power is going to be multiplication between those powers. So yeah, this is just going to be e to the ln x, or e to the ln a x. And then we could use our chain rule. Yeah, we can use chain rule for this one. So if f of x is ln a x, because ln a in this context is a constant. It's just a number. The derivative of this, well, x to the 1, x to the 1, that derivative is going to be x to the 1 minus 1 times 1, which is obviously going to be 1, because anything to the power of 0 is 1, so we are left with just ln a, and that, comes down pretty nicely to our e to the power of u times u prime, so we are left with ln a times e to the ln a x, which also again is e to the ln a to the power of x, which, as we define, this is a. So this is just going to be ln a times a to the x. And you can generalize this further. You can say that if u was some function of x, then you can make that x into a u, and then make that times u prime. But still, that is the derivative of an exponential function with a base other than e. And now I'll make good on my promise, and we're going to do some implicit differentiation. I'm going to do a couple of methods. I feel like we should get, a little bit crazy, or as crazy as we can with derivatives, which admittedly is not very crazy. But instead of using the same methods, like Pythagorean theorem for all three, we're going to use different methods of proving all three of these. Well, not different methods of all three, but we're going to try and come up with some different ideas to prove the same general concepts. And, if this doesn't work for you, if any of these don't work for you, then you can find like a billion proofs online. These are, not only are they good examples of implicit differentiation, they're also pretty easy to prove. So yeah, you can find a million examples if you wanted to. But we're going to start with, the one that you might see perhaps the most often, that being, arc sine x. And so we know that if y is equal to, actually, I won't use arc notation right now. If you don't know, arc sine, arc cosine, they all mean the same as like inverse, like sine -1x, not sine to the power of -1, but like just, it's like inverse notation. So sine -1x. I'm still gonna say inverse sine or arc sine, but yeah, I'm gonna keep this like inverse notation so that it might be a little bit easier to see what we're doing. If we say that this is an inverse of sine x, then using common sense, we can switch our inputs, and it should be the inverse of an inverse, which is just the original function. So if we swap this around, we would say that this is equivalent to x equals sine y, which, is a little bit easier to think about. We've seen this a little bit more often, but I'm going to be using Pythagorean's theorem. This could be considered unit circle, I think, maybe. Is this unit? No, this is not unit circle. Forget everything that I'm talking about. But Pythagorean's theorem. So we have sine y, which means that y is going to be our angle. And yeah, we're saying that x, which is presumably x over 1, is equal to sine y. And if y is our angle, that means that our opposite is going to be x, and our hypotenuse is going to be 1. Because, sine of anything is opposite over hypotenuse. So, yes, based on that, we can assume that the side opposite to the angle is x, and the hypotenuse is going to be 1. And if we have these two known sides, we can find this guy right here. We're going to call it A. And we're going to say that A is equal to, well, let me not skip any steps right now. We're going to say that A squared plus x squared equals 1. So therefore, A squared is equal to 1 minus x squared. And then A is equal to square root of 1 minus x squared. And people who might have skipped ahead and maybe seen what the derivative of an inverse sine looks like. Might already know where this is going, but for everybody else, we have, let me erase our original. I'll keep this triangle to make a point later on, but we have x equals sine y, and we're going to do some differentiation. We're going to try and find the derivative with respect to x of both sides, so d dx x, which I'm pretty sure I did like 2 seconds ago. It's just going to be 1 again, and then d dx sine y. We are going to say that, hey, y is a function of x, but this is just, in our imaginations. We're just thinking that, we're not going to explicitly define y as a function of x because that's what we're trying to find the derivative of. Not that, but sine minus 1x. If we were to explicitly define y as a function of x, then we would never be able to find this derivative. So we're going to have to use implicit differentiation. And so therefore, we're going to use ddx, which is ddx1, which is not ddx1, ddxx, which is going to be 1. And we're going to find the derivative of sine y. Let me actually go back to ddx notation. We're going to say that the derivative with respect to y of sine y times the derivative of y with respect to x. So maybe write that down, think about it. But I'm hoping that you've seen my other video. I'm not going to spend too much time talking about y, but still, 1 is equal to cosine y because that is the derivative of sine y. And we cannot forget our most important friend, dy dx. And now we divide both sides by cosine y. That side by cosine y, that side by cosine y. And then we get dy dx equals 1 over cosine y. And now we're going to use Pythagorean's theorem, which is, I think, an interesting concept. I saw this proof a little while ago, but still. This is a lot less intimidating than sine minus 1x, but I think it's equally perhaps confusing because what is y? Well, we said that y is sine minus 1x, so is our derivative going to be cosine sine minus 1x? Because that seems insane. We're going to use our original triangle right here. So we know that sine y is equal to x, and we know that a is equal to, let me rewrite that, we know that a is equal to square root of 1 minus x squared, and we know that sine y is equal to x, so therefore cosine y is equal to the adjacent side, or the side adjacent to the angle, over the hypotenuse of the triangle, which in this case is going to be square root of 1 minus x squared over 1, and anything over 1 is just going to be that thing, so we're stuck with 1 minus x squared, which means dy dx, or the derivative of y with respect to x, is equal to 1 over square root 1 minus x squared. And you might still be wondering about that y. Well, since our original equation, y is equal to the inverse of sine x, since that one is an explicitly defined function of x, we're cool. Dy dx is just going to be, you know, d dx of sine negative 1x. You know, this is the same thing as that. Dy dx only matters here because y is already explicitly defined. There's no crazy things happening. But still, the derivative of arc sine x is 1 over 1 minus x squared. And I would like to point to something interesting right here. As you might be able to see, well, I don't think you might be able to see it, but still, cosine is positive on this range. And since minus pi over 2 is less than or equal to y, which is less than or equal to pi over 2, is our range of values, or range or domain? I'm just going to say range because range can be anything. This means that cosine y is always going to be positive. It will always be a positive square root of 1 minus x squared. So that derivative of arc sine x is always going to be positive. And there's not any random cases where that would change. So yeah, we've got arc sine x down. And now, instead of using Pythagorean theorem as, common sense would dictate, we're going to use trig identities. So for this one, we are going to say y is equal to the inverse of, I don't know why I keep wanting to write arc cosine. I guess I like that one more, but I just want to fully make sure that, the switching of inverse values, like the switching of input values within inverse functions to uninverse it is, pretty apparent. So that can just become that, if we switch our input values and then use the inverse of the actual function, then the inverse of an inverse is just going to be that function. So yes, this is equivalent to x equals cosine y. And we're in a similar situation. We're going to do the derivative with respect to x of both sides because we're trying to find the derivative of y prime there. So yes, we're going to find the derivative with respect to x of both sides. So d dx cosine y and d dxx, which I hope by now we can just kind of intuitively say is 1. So 1 is equal to, again, we use chain rule. Since y is not explicitly defined as a function of x, we're going to have to find the derivative with respect to y of cosine y, and then we would multiply it by the derivative of y with respect to x. And so, again, don't want to spend too much time on that, but we know that this would be just negative sine y times dy dx, which means that dy dx, if you divide both sides by negative sine y, sorry, that was odd, then you would have negative 1 over sine y. And using a trig identity, we know that sine squared x plus cosine squared x is equal to 1. I don't think a proof for this is necessary. It's just a very common trig identity. But I mean, I don't know. I think it might be an interesting video to find some proofs for that because I can't remember having seen one. But yes, if sine squared I don't know why I erased that. If sine squared plus cosine squared equals 1, then sine squared x is equal to 1 minus cosine squared x. And then sine x, I should not have used sine x because I'm going to be confusing everybody else, but maybe I should make that into like a or something, just to make sure that I'm trying to say that this is how you would find sine x in terms of cosine. It's not like this isn't relevant to the actual thing. I just use x for everything. So sine y is equivalent to the square root of 1 minus cosine squared y, which, let's think, we have y equals the inverse of cosine x, which means that x is equal to cosine y. Isn't that the exact same thing as what we have here? And if you're thinking that, then pat yourself on the back. You are absolutely correct. X is equal to cosine y, so that means that cosine squared y is equal to x squared. So we're left with negative 1 over 1 minus x squared, which, if you remember, is just the negative of the derivative of arcsine, which is cool. I mean, all cofunctions, their derivatives are going to be negatives of one another. So, yeah, that's pretty cool, I guess. And now we are nearing our last, not our last, I think I'm going to do the derivative of a determinant, but yeah, we're going to do our derivative of arctan x. Let me write that down. And I think that this one is a fun one. We're going to go back to y equals tan minus 1x, or the inverse of tan x, which means that x is equal to tan y. And now we're going to, as always, differentiate both sides of the equation. It was the most bizarre d I've ever written. d dx x and d dx tan y. I'm hoping now you know what we're gonna do. Implicitly define y as a function of x, and then find the derivative of tan y with respect to y multiplied by the derivative of y with respect to x. So the derivative of x is 1, and that is equal to d dy tan y times dy dx. And now, again, this was just in my last video, but tan y is equal to, well, not tan y is equal to, but the derivative of tan y would be equal to secant squared y times dy dx. I should stop using x's for multiplication, but we're actually gonna do something kind of unique-ish to this one, but we're going to substitute this already in the first, well, not the first step, but we're going to substitute this in just a touch earlier than we might usually, and we'd say 1 is equal to secant squared inverse tan x times dy dx. And now we're still going to do our divided by both sides just to isolate, that's a good word, isolate our dy dx. Yeah. And once we've done that, we are going to use another, well, let me write it down. We're going to use another trig identity. I hope it's already kind of jumping out what we should do. I'll give you a hint. It's the only relevant one that uses both secant squared and tangent, so yeah, hoping it's kind of obvious, unless you don't know this identity, in which no blame. Secant squared, I'll use a this time. I feel like x might have been a tad confusing, is equal to tan squared a plus 1. That's just a trig identity. I might do some like introduction to trigonometry video and find some proofs of these identities, because honestly I have no clue. But with that, let's do, yep, we're going to do dy dx is equal to 1 over tan squared tan, or inverse tan x plus 1. So, because, it's, if this is going to be our a, and this is secant squared a, then that's still going to be tan squared a plus 1, which is why that's there. So, tan squared, wow, I mean, I think it's pretty obvious, but I might just write it slightly, obvious-er. Tan squared is equal to tan squared. So we can take out this squared and we are left with a function, and then that inverse of a function with an input of just x. So it's like saying, again, the square root of a squared is equal to a. You are doing some operation, which is squaring it, and then you are square rooting it, which means that you are doing an operation doing an operation tan, and then inversing it. So we are going to only be left with x, which means that our derivative for y equals secant x, not secant x, y equals the inverse of tan x. The derivative of that is just going to be 1 over x squared plus 1, which I think is, it's a pretty nice looking one. It's probably one of the easier derivatives, in my opinion, to remember. And, obviously chain rule can be used for any of these, like for the one that we just did. If f of x, oh, I'm not going to use f of x. If u is some function of x, and we are given the inverse of tangent for some u function of x, then you'd just be left with 1 over, well, not 1, u prime. Let me write that down. But it's just going to be, the normal derivative, 1 over u squared plus 1 times the derivative of u, so u prime. So yeah, those were the inverse trig functions. I think that's it for today. Let me see. Oh, yes, I wanted to show you guys the derivative of a determinant. Yeah, so I actually don't know a proof of this off the top of the head. I just know that the derivative, let's say, yeah, okay. I'm just going to use the a of t notation. So the derivative with respect to t of some determinant a of t is just going to be equal to the trace, which is the it's the sum of the elements on like the diagonal from the upper left to the lower right. That's the trace of the adjugate. And the adjugate is just the don't want to make it sound too complicated, but it is the transpose of the cofactor matrix. Like I don't know what it's called. I think it just can be like any letter. So like we'll say X. So it's the adjugate of A of t times, again, the derivative of A of t with respect to t. So already you might be able to see some similarities to chain rule, and if this looks like nonsense, that's cool. I will do some type of video on this in the future, and when I do, I promise, not this specifically, but I'll do some type of introduction to matrices, and when I do, I will try and find some proof for this, because I honestly just don't know. It's like an operation, so I think it'd be kind of like trying to prove multiplication. I mean, we can prove like derivatives and limits, so there probably is some type of proof for it, but yeah, just I don't know personally. Yeah, odd note to end on, but still, in the comments below, if you could find something. This is called Jacobi's formula. If you can find anything like a proof that you might want me to look at or to explain in some way, that would be cool. But yeah, music recommendation for today. I mean, so I've been really enjoying this album. Well, I mean, I've been enjoying it for a while now, and I wanted to recommend it, but I will be saving that for a slightly bigger video. I think this might be a little bit basic, but Led Zeppelin 3 by Led Zeppelin. Wait, is it 2 P's or 1 P? It's 2 P's. Okay. Led Zeppelin 3 by Led Zeppelin is honestly, and I'm not saying this to be contrarian, I'm not saying this to be like woke or whatever, Led Zeppelin 3 by Led Zeppelin is my favorite album from them. Honestly. I think their exploration of different genres like folk actually work really, really well. And it's almost genre defined. You have like songs like Immigrant Song, like these hard rock like bangers, and then you go to like, I don't know, Tangerine, Gallows Pole. It's like, I wouldn't say it's tonal dissonance, but just the wide variety of sounds that Led Zeppelin attempts to, and in most cases succeeds at trying to explore, it's just impressive. And honestly, it's my favorite album from them. I truly think it's pretty much perfect. I mean, like, I don't know. I think it's perfect. I don't think there's any skips. I think it's just a great album. And yeah, I know this has a bit of a stigma because I'm not too well versed in the history, but I know like it was like really hyped or something, and then like Led Zeppelin trying to explore different influences kind of tick people off. But still, I think it holds up incredibly today. And if you do choose to listen to this album, please comment down below. And if you wait, messed up my outro. God, this video has just been a complete mess. I probably ought to redo it. when I'm less tired. But yeah, if you enjoyed this video, please comment down below. If you learned something, also comment down below. If you did not learn anything and you did not enjoy this video, then constructive criticism is always encouraged. And if you're not in the mood for constructive criticism or a comment, then you can do some, trying to think. Let's say jump squats. Okay, bye.